Unit 2, Lesson 3, Exponential Functions should be a pretty quick one. Go ahead, read through this top part. The idea here being that linear, quadratic, and exponential are common functions we use all through high school. And exponential functions are especially useful in the real world because they are very common. A exponential has the general form f of x is equal to a times b to the x power. In this case, a cannot be equal to 0 because if you multiply 0, that'll just render everything else useless here. If I plug in a 1 for b, b cannot be 1 because that'll also turn it into a linear function because 1 to any power is always 1, so the x doesn't actually change anything there. In this formula, we will say that a represents the initial, oh my gosh, it broke. The initial amount. So a would be where you start. It's also the y-intercept. B represents the common ratio. So if you have a constant multiplier, that's what goes in for B. Now, take a look. Exponential growth will be increasing whenever a is greater than 0 and b is greater than 1. So any number more than 1 will just be multiplying, making it larger. If a is greater than 0 but b is less than 1, like a fraction, 1/2, that's going to make it decrease because the 1/2 will have the exponent. So 1/2 times itself over and over will make a fraction that's getting closer to 0. To demonstrate these, watch the camera there. To demonstrate these, I wanted to show just a couple quick graphs. It's kind of hard to see. Let's see if I can get it to focus. Come on. Can we see here? So the first one in blue will just be a standard 2 to the x power. Then for the red, I have a negative version of that. So blue and red should just be a reflection of each other. Then instead of having a common ratio of 2, I switch the common ratio to 1/2 for the next two graphs. The 1/2 means that rather than increasing, this will be decreasing or decaying. So let's watch. It's going to graph these in order on this screen. I just need it to focus. Come on, let's see if we can get this to work. There we go. Here we are. Ready? This is a standard. The blue would be a regular 2 squared. 2 to the x power. It's getting bigger and bigger really quickly. Now, if I throw a negative in front of that in the a value, then that would make it flip and it would be decreasing really quickly. Then if I switch, blue was 2 to the x power, 1/2 to the x power now is decaying. It's decreasing. And we're going to look at the end behavior here because we know from rationals, if you're getting a fraction with a bigger and bigger denominator, you're getting closer and closer to 0. Lastly, if I throw a negative in front of that, negative 1/2 to the x power, you'll notice that it is going up. It's just a reflection of that first decay. So that gives you an idea of how the parts of the equation play a role. Now, let's read through the rest of this table. I'll come back together on the next page and do a couple problems, but do not skip reading this. You should have read through that. Did you read the whole table? All right, time to get started on some examples then. So if you look right here, it asks us to write limit statements for each of these. If you look at this, the left side is going towards negative infinity, so the limit of a to the x power, that's just a standard exponential. As x approaches negative infinity, will be equal to, well, it's going to be getting closer and closer to 0. For the second one, the limit of the exponential as it approaches positive infinity is going to be equal to, well, that's going to be increasing forever, so that's infinity. Every single one of these will either be 0, infinity, or negative infinity. Try B. All right, check out the answers here for B. Did you get the same thing? If not, come in with some questions. I did want to talk about this next one because we got our A value equal to 5. Our B value is equal to 2/3. So the B value is the common ratio. If I keep multiplying 2/3 by itself, 2 will grow slower than the 3, so therefore this will over time become a smaller and smaller fraction, which means it's getting closer to 0. Now because it's A being 5, a positive value, I know that this decay will be above the axis. That's going to help me visualize this. So we're decreasing, we're above the axis. So on the left side, the limit of g of x as x decreases without bound, that is actually going up as you go to the left. So that'll go to positive infinity. The limit of g of x as x increases without bound, that's another way that you may be able to say that or see it on the test. Well, on this one, since it is a fraction that's going to get bigger in the denominator, it's getting closer and closer to 0. Now, let's go to example 2. I want you to take a look. We want to determine if the exponential is increasing, decreasing, and concave up or down. In this case, this is pretty simple. The slope is negative, but getting less and less negative, which means it is concave up. Concave up, though, is not necessarily meaning increasing because this is going down, so decreasing. Try B on your own, and then for C, think through the same thing that I did here. Maybe even draw yourself a sketch to answer this one. Ta-da! Check out B and C. If you have any questions on those, come in and ask. On example 3, it gives us selected values for f of x and wants to know if this function is linear, quadratic, exponential, or none of these. Well, my first instinct when I look at this is to check multiplication since we're talking exponential. But 3, 5, 9 doesn't have a multiplication pattern. However, we do have a constant addition pattern. Take a look. Now, you'll notice here that the second rate of change has a multiplicative pattern here. So if at any point you notice a multiplication, that means that this is a geometric sequence that's been transformed. So in this case, we do have an exponential function because we do end up with a multiplication that's just been shifted. Notice, if these numbers had been 1 less, 2, 4, 8, 16, that's our geometric pattern right there, but the y values are shifted up by 1. So, in this case, you would say f of x is exponential because it is a geometric pattern translated up 1. If at any point you find that multiplication, you know it is geometric. If this was quadratic, how would that be different? Great question. You would have a second rate of change that is a constant addition. So don't get those two confused. Otherwise, come in with questions on Monday.